All right, chemistry kids, this video we're going to go through the 1-1, 1-2 practice mini test or quiz, whatever you want to call it. It's the in-class quiz that you're about to take on 1-1 and 1-2. So we're talking about like significant figures, scientific notation, units, measurement, density, percent error, those concepts. Okay, so you have a copy of this quiz. You got it a couple classes periods ago. The answer key has been posted, so hopefully you've gone through it. But if just watching or just looking at and reading the key, if you still don't understand why, this video is here for you to see what you should be thinking as you go through the quiz. So the first thing, we're just going to go do a run through on the quiz itself, on the blank, and just kind of note a few things, and then we're going to go look at the answers to everything. Okay, so here we're just, this is, again, number one, just knowing the SI units for these different measurements. It's just memorization. I think the thing that you should have in the back of your mind, there's one SI unit that has a metric prefix, and that's for mass, and the rest of them are just base units. So by metric prefix, I mean something like milli, centi, deci, kilo, mega, tera, nano, all those are the metric prefixes. And so remember, mass is, the base unit for mass is grams, but the SI unit is kilogram, kg, kilogram. So that would be the one thing to remember. Temperature is a special one. Remember, it's Kelvin. Energy is one that maybe you haven't used in the past a lot. We will use it a lot later on this year, but energy is joule. And then the amount of substance. Remember, the way I wanted you to frame that was number of particles, count of particles, tally of particles. It's not the same thing as mass. A lot of students, if I asked the same question but I didn't put mass here, and that wasn't one of the things you were tested on, a lot of people will put grams for amount of substance, or maybe even a volume measurement for a unit for amount of substance. So remember, that's moles. Moles is the SI unit for amount of substance. Okay, so yeah. Here we're just taking a proper measurement. So remember, the first thing, don't even try to take a measurement. Read the ruler here in this case. Maybe it's a graduated cylinder. If it's a ruler, it's probably going to be centimeters. On the test or quiz, it'll tell you that it's centimeters. Here, I told you it was a centimeter ruler. Okay, so we're going with centimeters here. But remember, if it's a graduated cylinder picture that you're using to take a measurement, remember that would be milliliter is your unit. So remember, when you put your measurement here, make sure you include the unit. So if you want to, just write cm right here just to know, just to remember, all right? So as soon as you know what the unit's gonna be, put it over here, okay? And the first thing you're gonna wanna do is figure out how many decimal places am I allowed to round to? Am I allowed 0 decimal places, 1 decimal place, 2? So it's usually, can I estimate to the tenths place, or can I estimate the hundredths place? Especially in this class, that's really going to be the question. Should my measurement go to the tenths place, or should it go to the hundredths place? And remember, the way you figure that out is, again, don't look at the thing you're measuring, like this line right here, right? That's not the focus. The focus would be, what does each as increase in one of the graduation, as you go from one graduation to the next, one tick mark to the next, what is that an increase of? So like, as I go from this one to the next smallest one, here, let me zoom in so we can maybe see it. Okay, so as I go from this tick mark here to that tick mark, what would that represent? So we got to figure that out. Well, if this is 0 centimeters and this is 1 centimeters, and we got those lines in between, then obviously this is 0.1, 0.2, 0.3, 0.4. So each graduation is an increase of 0.1 centimeters. So since the graduations give me the tenths place, you need to estimate to the hundredths place. So before you even look at the measurement, you should be thinking, well, anytime I use this particular ruler, what decimal place should any of my measurements go? And if, in this case, this particular ruler, every measurement should have a hundredths place. So if you think it's just 5, you need to write 5.00, or it wouldn't be a proper measurement with this ruler, okay? Let's just, and again, we're going to go through all the answers. Things to think about. So here we're given 3 different trials. So you're probably going to be asked to calculate an average. When you do multiple trials, your experimental value that you're going to use is the average of your trials. We're asked about accuracy. Remember, to determine if you're accurate, you have to know what the true value is. If you're asked about precision, remember, precision, you don't need to know the true value. You only need to compare the measured values that you have, the experimental values, your trial values, and how they compare to each other. Okay? Hopefully, we're good at calculating an average. All we would have to do is add our 3 trials up, and in this case, because there were 3 trials, divide by 3. Okay? And then we got to be able to calculate percent error. And so the thing to remember is, if you're given multiple trial data and then you're asked to calculate percent error, remember you need to have an experimental value. That's your value. And if you have multiple trials, you're not going to pick any particular trial as your experimental value. You're going to use the average. So your answer in part C here, the average density of your 3 trials, that would be your experimental value when you go to calculate percent error. Okay. Here, it's finding the density of an object through water displacement. So remember, this can be tricky because you need to take the mass of the object, which is given to you here, and you have to divide it by volume of just the object. So to get the volume of just the object, remember, you would have to do this volume minus that volume, right? This is the volume of the water, this is the volume of the water, and the object. The difference between those values would be the volume of the object. And this is where we're going to have to really be careful in terms of sig digs, because when we do the subtraction, decimal places, but then when we do the division to get the density, significant figures we got to worry about, okay? So then moving on here in part 5, all we're doing is reporting how many sig digs these measurements have, so that should be really easy, okay? Here we're just doing calculations, so we got to be aware, are we multiplying or dividing, or are we adding or subtracting? So if we're adding or subtracting, we should be worrying about decimal places. If we're multiplying and or dividing, we should be worrying about significant figures, not decimal places, but significant figures, okay? And then we also have to get the proper units. So this is where it could get a little tricky. So, fill this in right away. Just fill the units in right away. And then you can come back and do the math and round to the proper number of decimal places or sig digs. So if you're adding centimeters, this is just going to be centimeters, so I'll just write centimeters here. If you're multiplying centimeters times centimeters, that would be centimeters squared. So over here, I'd write centimeters squared. Remember, if it would be centimeters times centimeters times centimeters, that would be centimeter cubed. But if you're just adding centimeters, it's just centimeters. If you're adding grams, it's just grams. Okay. So this one would just be centimeters, this one would be centimeters squared, and then we're doing grams divided by milliliters, and so that would be grams per milliliter, but the way you would write that is G/ml, right? Grams per milliliter, okay? And then here we're just taking a number and we're converting it to scientific notation, but we are also rounding it to a certain number of sig digs. So we gotta have the right number of sig digs and put it in proper scientific notation, and that's what we're doing here, okay? Now, I'm not going to have this conversion on the actual in-class test, but remember, we did go over it in class once, but it's not something that we've really discussed a lot and done a lot of practice. But to go from Celsius to Kelvin, all you do is add 273. So 273 is the number that you add to degrees Celsius to turn it into Kelvin. So all you would have to do for this one is 25 plus 273. That equals 298. So the answer to here would just be 298. Capital K for Kelvin, okay? So that's kind of the thought process for each thing, and then now let's go check the answers and see how you did, okay? So the SI unit for mass is kilogram, kg. The SI unit for volume is liter, okay? And notice, kilo is a metric system prefix. The only SI unit that has one of the metric system prefixes in it is for mass. Everything else is just a base unit. So it's not milliliter, it's not centiliter, it's just liter, right? It's not kilokelvin, it's just Kelvin. It's not kilojoules, it's just joules. So the only one that has an SI unit, a metric prefix is mass, kilogram. Okay, so volume is liter, Kelvin is temperature is Kelvin, and that's capital K. And notice it's not degree sign K. So like degrees Celsius is, the degree sign and then Celsius. Degrees Fahrenheit would be degree sign and F, but Kelvin is just K. And you don't say degrees Kelvin, you just say Kelvin. All right. Energy is joule, capital J. Time is seconds, S. And again, amount of substance, count of particles, number of particles is moles, and the abbreviation is just MOL. So MOLE, mole, MOL is the abbreviation. Okay. So remember, this measurement had to go to 2 decimal places. So again, many acceptable answers for this measurement. Remember, that last digit is an estimated digit. Okay, so it's not going to all be the same. The main thing is here that you knew to go to 2 decimal places. So again, if you were measuring this and you thought it was right on the 5, and you just wrote 5 centimeters, that wouldn't be a proper measurement given the precision of this ruler. You have to say 5.00 if that's what you thought it was. But you couldn't say 5.000. That would be too far of an estimation. Okay, and then obviously put the unit, centimeters in this case. Okay. So here again, so they give us the actual density. Okay, so that's what the density should be, and then these were our 3 densities that we measured for the object. And so in terms of accurate, we're not very accurate, right? The density is 11 grams per milliliter, and we got, like 13.5 grams per milliliter. We're not very accurate, okay? But in terms of precision, we are pretty precise because we almost got the same answer each time. We almost got the same result each time. That's precision, okay? So we are pretty precise, but not very accurate because we're far off from that value, okay? The average, if we added them up, it just comes out to be 13.54. You probably could have done that one in your head, but remember, add them up and then divide by 3 in this case. And then this would be our experimental value. And so this is going to be our percent error. Now, how do we do that? Remember, we do the difference between the 2 values. So remember, it's the absolute value. So you could do experimental minus true or true minus experimental. You're taking the absolute value, so it doesn't matter which one. You just have to remember you divide by the true value. So you're dividing by this. So it's going to be 13.54 minus 11.34, and then whatever that difference is, divide it by 11.34, and then multiply it by 100, and that gives us our percent error. Okay. All right. So this is the tricky one, right? So this is essentially what we did in lab. We took 3 measurements of our metal. We found the mass of the metal. Then to figure out the volume of the metal, we first got volume of just water. Then we put the metal in the water. Obviously, it displaced the water, right? We call it water displacement. And this was the volume of the water and the object. So if you do 32.7 minus 25.2, that gives you the volume of just the metal. And that's what we want, because we want to find the density of just the metal. So we need the mass of just the metal divided by the volume of just the metal. Okay. But this is where we got to remember our rules for significant figures in different types of calculations. So here, we're going to take these 2 measurements and subtract them to get the volume of the object, in this case. But remember, when you subtract, it's about decimal places. So my 2 volume measurements only went to the tenths place. So my answer to this mathematical operation has to go to only the tenths place. So it's 7.5. So notice we take 2 measurements, right, that each have 3 significant digits. But when we do the subtraction, the difference ends up with only 2 significant digits. Because again, when you add or subtract, it's not about sig digs, it's about decimal places. When you subtract, you could end up, not always the case, when you subtract, you could end up with less sig digs than some of the numbers you started with. When you add, you could end up with more, okay? But again, it's not about sig digs, it's about the decimal places. So now, that would be the volume I report for the metal with the correct number of decimal places, Okay, but then to get the density, it's going to be the mass, which has 4 sig digs, divided by the volume of just the metal, which only has 2 sig digs. So when I do my mass divided by volume, I have to round that answer to only 2 sig digs. So that's why my density is 1.5 grams per milliliter. That's why I can only report 2 significant figures. Okay, so we'll keep on going. All right, here we're just identifying sig digs. So remember, these leading zeros, never significant. And this 0 is significant because we actually see the decimal point. Okay, so trailing zeros significant when you see the decimal point. So that's significant because I see it. And then captive zeros are always significant. So this has 4 sig digs. Right, scientific notation, it's just the digits in front of the multiplication sign. You don't have to put it in the standard notation. It's just what those digits are. If I wanted to take the same number and give it a 4th significant digit, I could just put a 0 here. Okay. If I wanted to take away a sig dig, it would be 6.0 times 10 to the 23rd, and that would be 2 sig digs. Okay, so you don't have to go out of scientific notation or back into scientific notation to figure out the number of sig digs. Okay. Well, the thing is about going back and forth from scientific notation to standard notation is you need to maintain the correct number of sig digs. So if I wanted to put this number into standard notation, I would want to make sure that when I report it in standard notation, it only has 3 significant digits, because that's how much it's starting with. Okay. Then over here, captive zeros always significant, so all those digits are significant. And then remember, it doesn't matter about decimal points for leading zeros. That doesn't matter. So leading zeros, never significant. So it's only the 2 that's significant in that measurement. Okay. So here, doing the math. So first off, units, right? Centimeters plus centimeters plus centimeters is centimeters. Okay. Centimeters times centimeters is centimeters squared. Grams divided by milliliters is grams per milliliter. Grams/milliliters. Okay. But now let's talk about the math. Okay. You add them up, and the reason why I'm rounding to 1 decimal place is because this only had 1 decimal place. Okay. So when you add or subtract, it's about how you're limited by decimal place. Okay. Here we're multiplying, so we're worried about sig digs. We should recognize that this only has 2, while this has 3 sig digs. So we have to round our final answer to just 2 sig digs. Okay. And then we're dividing, same rule. It's the sig fig rule when you multiply or divide. So our mass measurement has 4, but our volume measurement only has 2. So we're going to have to round to 2 sig digs. Okay. All right, so the first thing I did here was just we want to report the measurement in scientific notation, okay? But we also want to round it to 3 sig digs. So the first thing I did was round it to 3 sig digs, okay? So the way you would do that is you would say, okay, 1, 2, I take my 3rd digit, I use my 4th digit to round that up or down. That 0 would round up to a 1, and then I got to have my 0 placeholder. So this number rounded to 3 sig digs is there, and then to convert it to proper scientific notation. Remember, proper scientific notation means 1 digit to the left of the decimal point. So you would start here, and you would go 1, 2, 3, 4, 5, 6, 7, 8, 3.131 times 10 to the 8 milligrams. Okay. And this one, we're taking it out of scientific notation, and we're putting it into standard notation, but then we're rounding it to 2 sig digs. So I took this number, I took it out of scientific notation, and right now, like it has 4 sig digs here, it still has 4 sig digs, but now I got to round that to 2 sig digs. So this is a case where, okay, 1, 2, the 8 is going to round the 9 up to a 10, so that 9 is going to become a 0, but then you got to put a 1 on top of the 2, and the 2 is going to become a 3. So it's going to end up being 0.000030, and that would be 2 sig digs, because remember, this 0 is significant because we have the decimal point there. Okay, trailing zeros are significant if you see the decimal point. Okay, and then again, remember, the magic number for the Celsius to Kelvin conversion is 273. If you're going from Celsius to Kelvin, you're adding 273. If you're going from Kelvin to Celsius, you're subtracting 273. That's it. So since I have 25 degrees Celsius, I would take that number 25. I would add 273, and I get 298. And the units for Kelvin are capital K. All right, so I hope you feel good. We did more practice in class, and you got all those Schoology assessments that are going to be helpful and benefit you. Okay, so make sure you review the night/morning of the mini test too. Remember, it's a mini test, or you can call it a quiz, but it's a summative assessment. So we're calling it a mini test. It's probably going to be, a 10 to 15 minute little test that we have at the start of class, and then we're going to be moving on. Okay, so our unit tests tend to take the whole class, or you'll have the whole class to do it, but the mini tests, they're pretty short and they shouldn't take too long. Okay, so you need to know the stuff, but it's not like a lengthy thing you have to really worry about too much. You just got to make sure you review. Okay, so have a wonderful day.